In this video, we're going to discuss the concept of recursion. So recursion occurs when a thing is defined in terms of itself or of its type. Recursion is used in a variety of disciplines ranging from linguistics to logic. The most common application of recursion in mathematics and computer science, where a function being defined is applied within its own definition. While this apparently defines an infinite number of instances, it is often done in such a way that no loop or infinite change of references can occur. So, a function that is defined in terms of itself is called recursive. Here's an example. Int f of x, which takes the parameter int. If x equals 0, return 0. Otherwise, return 2 times f of x minus 1 plus x times x. So, this is called the base case. And if the value is known and it's without having to resort to recursion. So, in this case, we return 0. We need a base case because if we don't have it, we're not going to stop the recursion. We'll have an eternal loop, endless loop, and we'll get what's called a stack overflow. In fact, that's where the page got its name. So, recursion will continue to call itself until the base case is reached. What value could we pass this function that would prevent the base case from being reached? Take a hint. Well, it's always counting down and 0, but what if we pass something less than 0? It will never get to 0. So passing a negative number will put you in an infinite loop. So let's take an example. We're going to start with 4. If we call it with f sub 4, I'm going to step in. Is x equal to 0? Nope. So we're going to turn 2 times f sub 3 plus x times f. This works out to 2 times f sub 3 times 16. F sub 3 is 2 times f sub 2 plus 9. F sub 2 is 2 times f sub 1 plus 4. And f sub 1 is 2 times f sub 0 plus 1. So the base case will return 1, which we then plug into f of 1, which will give us 2 times 1 plus 4, which is 6. Then we take 6 and we plug it into f of 3, which gives us 12 plus 9 equals 21. And we plug f of 3 into f of 4, which gives us 58. So here are the rules. The base case. You must always have some base case which can be solved without recursion. We make progress. For cases that are to be solved recursively, the recursive call must always be making progress towards the base case. So here's an example. We've got f equals, here's our same example before. If we put in negative 1, what's going to end up is it's going to go negative 2, negative 3, negative 4. It's never going to hit this base case, and we're screwed. You must always have some base cases which can be solved without recursion. We must make progress. And the design rule is assume that all recursive functions work. And the compound interest rule. Never duplicate work by solving the same instance of a problem with separate recursive calls. That leads to what's called dynamic programming as an option. So, in this case, an exponentiation function, if n equals 0, return 1. Otherwise, return x times x and n minus 1. What is the base case? This is the base case, n equals 0. What does this look like in code? If n equals 0, return 1. So what is making progress? X times x of n minus 1. And what does this look like in code? If n is greater than 0, return x times f of n minus 1. So here's the full function. So if we call it with 2 comma 2, power 2, we'll call it with 2 times power 2 comma 1. 2 times 2 power 0, which is 1. So we get 4, which feed back in, and we get back 4 is our final answer. So here's an example. We've got the recursive version and the non-recursive version. Why do we want to use recursion? Well, this one looks more like the actual definition. So there's different types of recursion. There's tail recursion, which only uses recursion at the last end of the function. Non-tail recursion is a recursive call that's not tail recursion. Indirect recursion is a recursive call that calls itself via calling another function. Nested recursion is a recursive call that is not only defined in terms of itself, but also is used as one of the parameters to itself. And excessive recursion is a recursion that calls itself multiple times as part of the recursion. It gets messy. So let's take another example from math, the Fibonacci numbers. We've got f of n minus 2 to the n plus fib of n minus 1 if n is less than 2. So our code for the first part looks like if n is less than 2, return n. Otherwise, return fib of n minus 2 plus fib of n minus 1. So let's look at a small application. How do we find the greatest common divisor of two non-negative integers, a and b, that are not both 0? And what's the greatest common divisor? The GCD of a and b is the largest integer that divides evenly into both. Euclid, for example, 10, the largest one is 4 and 2. 4 and 12 is 4, etc. Euclid developed a recursive algorithm to calculate GCD of AB. The base case is if b equals 0, the result is A. Otherwise, return B and A mod B. And this makes us move towards our base case. So in this example, let A equal 54 and B equal 30. First time we call it, A equals 54, B equals 30. The second time we call it, B equals 30, and B equals A mod B, which is 24, and so forth. The next stopping condition is when B hits 0. So let's implement it very quickly. If B equals 0, return A. Otherwise, return GCD of B and A mod B. It looks just like the math equation. Can we use recursion other than for math? Can we reverse a string? Well, I'm going to leave that to you for a homework assignment.